Welcome to SMPLX Application Integrations. We'll be looking at how you can use SMPLX in Blender, Unity, and Unreal Engine. My name is Joachim Tesch, and I'm working as a software engineer with focus on real-time graphics at the Max Planck Institute for Intelligent Systems. I'll be your tour guide for this presentation, and in case I'm losing you, then please look for the man with the red and white umbrella. We'll start off with Blender and a short overview for those who haven't used Blender before, so that you see a bit what's possible with this application. Then we'll have a close look at the SMPLX for Blender add-on, which we released in May 21. We'll be looking at download and installation, the feature set, and finish with a couple of examples how you can use the add-on. After Blender, we'll be moving on to the Unity game engine, where we start with an overview again for those who haven't worked with Unity before. We'll look at the new SMPLX for Unity package, which we released in June 21. Again, we'll look at the features and at some examples what you can do with the application. Finally, we'll be looking at Unreal Engine. We start with the overview for those who don't know Unreal Engine, and then give an example of a typical data workflow to get data from Blender into Unreal Engine. Finally, we'll be looking at some work which was published at CVPR 21, where we use SMPLX and Unreal Engine. What is Blender? Blender is a free and open source 3D computer graphics toolset, which allows you to do 3D modeling, posing of skeletal meshes, rendering, compositing, and also other things like video editing. It allows you to render out images and video sequences, either using the fast physically based rendering method in the Eevee renderer, which runs on a GPU, or the slower path tracer cycles, which can run either on CPU or GPU, which can make really beautiful images. You can use Python scripting to enhance the editor user interface and to automate tasks. We're using this in our SMPLX for Blender add-on, which you'll see soon. While Blender's user interface has been a bit intimidating in past versions, we're very happy to see that 2.8 introduced a major user interface rework, and it's now much easier to use for newcomers than before. Blender is now also an established tool for indie and professional productions. This was highlighted by the animation industry at the 2019 Annie Awards, where Blender creator Ton Rosendahl received the UB/Ibrax Award for technical achievement on behalf of the Blender software. To make it easier to use SMPLX in Blender, we released in May 21 a dedicated Blender add-on on the official SMPLX website. The requirements are Blender 2.8 or later, and it is very easy to install. We'll look at that in a few seconds. There are no additional dependencies, and it uses right now the SMPLX model 1.1 with 10 shape components and 10 expression components. Everything is represented as a morphable model in native blend format, which allows you to integrate it very fast into existing Blender scenes. While Python coding experience is not needed to use the add-on, you can use the Blender Python API to access the functionality of the add-on for automation tasks. Let's have a look at the SMPLX Blender add-on feature set. It allows you to add the female, male, or neutral model in less than 1 second into the Blender workspace. The models are already set up with a UV map, which makes it easy to map textures onto the bodies. The add-on includes sample female and male textures, which were provided by Meshcapade under Creative Commons non-commercial license. You can auto-calculate the weights for the corrective pose shapes for the current pose. It's possible to set the body shape from height and weight values. This allows you to observe the effects of changing weight for a body of given height. You can quickly pose a body by loading in an external pickle file, such as the ones which were provided by the Agora project, where you have access to over 3,000 different body poses. Additional functionality includes the ability to position the feet easily on the ground and to export the data to other third-party applications like Unity. The add-on is written in Python 3, and the code is open sourced under GPL v2 license, so feel free to modify. If you're interested to try it out, then please register and sign it at the SMPLX website. You will then see a link at the top which will take you to the downloads area where you can download the Simplex Blender add-on to your local hard drive. Now let's start our Blender, install the add-on, and look at the features. Since everything is contained in the add-on, installation should be a very pain-free process. All you do is you install the zip file which you've previously downloaded and activate the add-on. The new user interface is then visible in the Blender sidebar. Let's see how long it takes to add some models. Let's add the female model and move it a bit to the side. Next we'll add the male model. Move it over to the right, and then finally the neutral model. As you see, it's very fast to add these models into Blender. We can use here the functionality to snap to the ground plane to make sure that the feet are properly positioned on the ground. We're able to set textures on the models. These are the sample textures provided by Meshcapade. Let's take a look at shape-related functionality. After you select the skinned mesh, you can randomize the body shape. Note how we automatically recalculate the joint locations. You can also manually change the body shape, and when you're done, recalculate the joint locations. We are now changing the body shape by setting new target values for weight and height. After setting a weight of 80 kilos, we specify the new target height and apply it to both female and male body model. Both models fit nicely in the available space above the head. The Blender Shape Keys panel shows you the calculated beta values for the given height and weight. We are now keeping the height fixed and use different weight values for the male model to observe the resulting changes in body shape. Similar to the body shape, you also have the ability to randomize the face expression. Let's see now how we can change the body pose. We have presets for flat and relaxed hand poses. Let's use now the Blender Pose Editor functionality to change the pose of the left arm. We select the left elbow joint and rotate it in real time and update the pose correctives with our add-on. Then we do the same thing for the left shoulder. Again, we rotate it and update the pose correctives. You can use the Load Pose functionality to quickly load in predefined body poses. These include over 3,000 poses, which are provided as part of the Agora dataset. Now that we found an interesting pose for our SMPLX body model, let's put it in a high dynamic range environment and render it out as a high-quality render with a Cycles path tracer. Now that we've seen the features of the add-on, let's look now what you can do with it. And I first want to hand over the microphone to Andrew Price. He's also known as Blender Guru. He does fantastic Blender tutorials, which are highly recommended, and he wants to tell us something about architectural visualization.
I just pull the camera until it's in the room and then just scale out the room till I can see the other walls that I want to see, basically. Now, if you were to start modeling here, the doors and the windows and things, You could very easily screw it up because it's not clear from this what the scale of it is. We know the scale of the ceiling and everything, but there's a reason that concept artists and architectural planners put in a human scale model. It's because it helps you to understand the scale of the scene. So
to better understand what Andrew means with this, let's try it ourselves. So we start by downloading a free model of a city parking garage from the internet. This is the model in Blender. And if we start to inspect it, we have the feeling that looks pretty good. The ramps seem to be a bit steep, but overall we get the feeling that the scale must be all right of that model. Let's add a human body to see if that's really true. So now that we've added our average male SMPLX model, we see right away that there's something wrong with the scale of the garage scene. It would be very uncomfortable to walk up those stairs, so we clearly need to do some scale corrections on that scene to match up with the human proportions. This classroom scene was modeled properly to human scale, and we see that everything is all right by adding our SMPLX model. Similar good situation here in the Barcelona pavilion scene, where also the human matches up nicely with the props and the environment. These architectural visualization examples have shown us that human body models like SMPLX can help us to understand the scale of the scene. In our next example, we look at keyframe pose transitions, which allow us to blend between two known body poses. You can use those in target scenarios like the generation of new body pose data. We'll start off with an empty Blender scene where we add the male SMPLX model and apply a sample pose to it. Then we select the rig and we keyframe the joint locations at frame 1. Then you advance in the timeline to frame 150, load in a different pose, and again keyframe that pose into the timeline. Afterwards, we can scrub along the timeline to sample new body poses. Once we have our selected target pose, we can update the pose correctors. In our third example, we'll be looking at the generation of a simple crowd with randomized shape and expression, texture, and gender. We'll be using Blender Python scripting to automate this task. Here we have Blender in the scripting workspace. To make things simple, we'll just place the bodies in a uniform grid. Let's now launch the script, and while it's running, look at the main function. We're looping over the list of generated locations. Pick a randomized gender, randomize the hand pose, and then add the model to the scene. Afterwards, we randomize the texture, shape and expression, and finally snap the feet on the ground and place it in a location with randomized yaw. If we're not happy with the current body shapes, we can launch another simple script, which is randomizing the shape of all the people in the scene again. We can now switch to Material Preview mode to see how everything looks with textures, and then start our final high-quality image render with cycles. In our final example, we'll be looking at the brand new geometry nodes, which have just been introduced in latest Blender versions. They will allow us to procedurally generate instance geometry on SMPLX mesh surfaces. Sample target scenarios include the generation of test data, where you could simulate varying clothing thickness, as well new media art if you want to explore your inner artist. Here we have the average female SMPLX mesh at the top. The surface of this mesh will serve as the input for the geometry node system, which you see at the bottom. The node system is sampling the surface, and for each sample it generates an instant sphere where the scale of the sphere is varying over time. Let's look at the output for the first frame and then observe it over a range of time. This concludes our overview on how you can use SMPLX in Blender using our custom add-on, which is available on the official SMPLX website for download. We hope it makes life in Blender easier for you, and feel free to share your experiences with us. Now we'll have a look at the Unity game engine and see how you can use SMPLX in that environment. Unity is a commercial real-time 3D game engine. It's very popular for mobile game development, and if you download a game for your iOS or Android device, chances are high that it was made with Unity. It is completely free for personal use. If you want to use it at the workplace, and you're working for an academic teaching institution, you should also be able to obtain a free academic license. The Unity Pro license allows you to commercialize your work. You can sell then your product for money, and you do not have to share any revenue back to Unity. It was first released in 2005 as a Mac OS exclusive game engine and has later been ported to other operating systems like Windows and Linux. Originally, there were 3 language options to script behavior in Unity. That included JavaScript, a Python-like language, and C# scripting. Due to the easy access of the C# framework and its collection classes, C# has established itself as the language of choice in Unity, and the other 2 language options have been removed from newer Unity versions. For many years, there have also been visual scripting solutions available as commercial products in the Unity marketplace. And in March 2021, there's finally also an official scripting solution from Unity available in 2021.1 and later releases. The main motivation behind these node-based systems is that also non-programmers can make games. One of the biggest advantages of game engines like Unity is that you can release to multiple target environments. You just use C# to write your behavioral code, and then you publish to Windows, Mac OS or Linux, as well as mobile operating systems like Android and iOS. We're very happy to see also out-of-the-box support for virtual reality and augmented reality devices in Unity, which makes it possible to quickly prototype new ideas in VR and AR. To make it easier for you to use the SMPLX model in Unity, we've released in June 2021 under the SMPLX model license a dedicated Unity integration on the SMPLX website. In order to use it, you need to work with a Unity long-term support release 2020.3 or later. In contrast to Unity 5 or older, blend shape weights outside of the 0-1 range are supported, which allows us to directly establish a mapping between the beta shape values and the Unity blend shape weights. Similar to the SMPLX for Blender add-on, we put an emphasis on easy installation. Everything is contained in the package, and there are no additional dependencies. It's based on the SMPLX 1.1 model with 10 shape components and 10 face expression components. The body models are represented as morphable models in native Unity format, which allows us to quickly add them to the Unity scene. Although no coding experience is needed to use the model in Unity, you have of course access to the functionality through the C# interface. Here's a quick overview of the feature set of the SMPLX Unity integration. You can quickly add the female, male or neutral model. They are already properly set up with a UV map, and we provide textures and predefined materials to help you setting up the appearance. The pose-dependent weights for the corrective pose shapes can be auto-calculated. With a click of a mouse button, you can position the feet on the ground, and it's possible to randomize the shape and face expressions. We provide options to change the pose. The hand can be changed between flat and relaxed pose. The body can be changed between T-pose and A-pose. A custom Unity Inspector graphical user interface exposes all this functionality so that you can use that without writing any code. All the code is in regular Unity C#, and we provide the source code if you want to modify it to your needs. Let's start up Unity and the SMPLX project to explore the features. Let's start by adding the female, male and neutral SMPLX models to our scene. As you see, it's a simple matter of drag and drop to get the model into the environment. Now we turn on the ground plane visibility to validate the floor contact. We then assign our predefined textured materials to the neutral, male and female mesh. For the male and female mesh, we use the materials with albedo and normal texture. Now we duplicate the female mesh and assign it a material with just albedo texture to see the difference. Then we enter the editor play mode and make real-time changes to the directional light to see how it affects the bodies. Notice the effects of the normal maps and the center two models, which create the illusion of a high polygon mesh. Now we show you how you can use the custom user interface to modify shape parameters. After selecting the model in the hierarchy, you'll then see the SMPLX custom user interface in the Unity Inspector. Let's turn on the joint positions. Now we randomize the shape parameters. Notice how the joint positions automatically recalculated and how the feet of the model are still remaining on the ground. We can fine-tune the shape parameters and manually update it. Let's randomize now also the shape of the male and female model. Modify the facial expression, we provide similar functionality in the custom user interface, which allows you to randomize, set, and reset the shapes. A quick way to change the body pose is to use the predefined pose templates, where we have the option to switch between a flat and relaxed hand pose. You can also switch anytime between A pose and T pose. Now we're using the pose functionality of the Unity editor to change the jaw pose. To better see the eyes, we're adding now a texture. Then we're rotating the eyeballs to change the gaze of the model. Let's manually pose the body now. We start off with a random shape. Then we manually pose the left arm using forward kinematics. We select the shoulder joint and apply a rotation. Then we do the same thing for the elbow joint. Observe the unrealistic crease on the left elbow. which can be fixed by applying our pose correctives, which is just a mouse click away. Our previous look at the SMPLX for Blender add-on already showed us some examples what you can visually do with a SMPLX model in 3D environments. In contrast to Blender, Unity is a real-time graphics engine. This means that you're not pre-rendering your content, but that it's generated at runtime. For desktop setups, this means that you're able to achieve a stable frame rate of 60 Hz, 144 Hz or 240 Hz depending on your connected monitor. For modern VR systems like the Valve Index or Oculus Quest 2, this means that you need to be able to produce stereoscopic content at a solid frame rate of 120 Hz. Let's examine how well the SMPLX model is running in Unity. We've used the SMPLX Unity integration to set up a very simple synthetic benchmark. All data was captured on an Intel Xeon workstation with NVIDIA RTX 3090 GPU. We'll first look at the default male mesh in T-pose to see the baseline on how fast the SMPLX model can run in Unity. We'll then investigate how the amount of active blend shapes affects the frame rate. We first activate all 10 body blend shapes by setting their weights to a non-zero value. Then we activate all blend shapes for the facial expression. Finally, we activate all 486 pose-corrective blend shapes. We then animate all 506 blend shape weights over time to prevent the engine from doing any optimizations through data caching. Please note that this example is not trying to produce realistic bodies by setting proper blend shape weights. The goal is to measure the effect of the active blend shapes. Without any active blend shapes, we can render the SMPLX model in 0.3 milliseconds. This corresponds to a frame rate of over 3000 frames per second. Let's activate now the 10 blend shapes for shape and afterwards the 10 blend shapes for facial expression. Only after activating all the pose-corrective blend shapes, we see a massive impact on frame rate. We now need 2.2 seconds to render a frame. Let's now add more SMPLX bodies to see how this affects the overall frame rate. We can quickly see that for crowd scenes, it becomes important to reduce the amount of pose-corrective blend shapes. If you want to use SMPLX characters for crowd scenes, you might want to disable pose correctives for distant characters since they have a small on-screen size. This concludes our section on how you can use SMPLX in Unity. Our custom SMPLX Unity package is available on the official SMPLX website for download. Let's now look at Unreal Engine and see how we use our SMPLX body models in that game engine. Unreal Engine 4 was released in 2014 and represents the fourth generation of the Unreal Engine, which dates back to 1998. It's used by many AAA games to produce stunning gaming visuals on both PC and console hardware platforms. Unreal Engine is developed by Epic Games, who used this game engine to build Fortnite Battle Royale. The total revenue for that massive multiplayer video game had already reached more than $9 billion by the end of 2019. Unreal Engine is free to use for non-profit research, and it doesn't matter if you're working at a teaching academic institution or at a general non-profit research company. You can also build commercial products, but keep in mind if your lifetime product gross revenue exceeds $1 million, you have to share profit with Epic Games. What makes this engine really interesting for research is that the full source code of that game engine is available on GitHub. You can study what algorithms are used in an industry-grade application and how are they efficiently implemented. If you run into a critical bug, you have the chance to fix that yourself. The working environment is the Unreal Editor, which is available as native downloads for Windows and Mac OS, or can be built from source on Linux platforms. The editor can be automated with Python 3 scripting, which is tremendously useful for import and export data pipelines. The runtime behavior can be controlled through either compiled C++ code or through a visual scripting system, which is called Blueprints. Similar to Unity, many target environments are supported for final deployment, which includes Windows, Mac OS, Linux, as well as mobile operating systems like Android and iOS. Again, we're also very happy to see native support for VR and AR devices in Unreal Engine, which helps cutting down on development time. Let's look now at two examples of published research work where we use SMPLX meshes in Unreal Engine. Our first example is Agora, avatars and geography optimized for regression analysis. It has been accepted into CVPR 21, so you have a chance to find more about it during the conference. We used Unreal Engine 4 to render over 17,000 synthetic images at 4K resolution. We use a collection of over 4,000 commercially available high-quality textured human scans to render 5 to 15 people in each scene. We fitted our SMPLX body model with face and hands to all of these commercial scans and imported them in Unreal Engine, which you see at the bottom right. We can now replace the commercial scans with our SMPLX fits and re-render all scenes. This allows us to illustrate the ground truth which we provide along with the images. Our second example is the POSA project, populating 3D scenes by learning human-scene interaction. The paper will be presented at CVPR 21. POSA uses SMPLX model fits to commercial posed body scans as a proxy to find the most likely placement in a 3D scene. In the bottom left image, you see an example where we use Unreal Engine with a real-time ray tracing to render an indoor apartment scene. All SMPLX models you see in that scene were automatically placed by the POSA system. We can then swap out each SMPLX proxy for its original 3D body scan, which you see in the right image. We also like to release a SMPLX plugin for Unreal Engine 4 in the future, but we do not have an exact release date at the moment. Now we're going to show you how you can get data from Blender into Unreal Engine. For this, we'll be using the free Send to Unreal add-on for Blender, which was published by Epic Games, the company behind Unreal Engine. The main job of the add-on is to make it easier for you to transfer data between Blender and Unreal Engine. It's available for free on the Epic Games GitHub repo. Please remember that it's a private repository, so you first need to connect your Epic account with GitHub to be able to access it. Once you selected your models for export and start the export process, it will export from Blender to FBX with the correct settings for Unreal Engine in the background. This includes static and skeletal meshes, as well as materials and textures. It then automatically imports the exported FBX files into the running Unreal Editor instance using remote Python code execution. Let's look now at a sample workflow where we pose a SMPLX mesh in Blender and export it to Unreal as a static posed SMPLX mesh. Let's start in Blender with a sample posed SMPLX mesh. We first make some adjustments to the head pose as well as the jaw pose. Let's tweak now the face expression a little bit. Yep, this looks good for now, and I think we're ready to start our trip into Unreal Engine. First, make sure that we have the corrective Shape Keys add-on enabled. This will allow us to quickly bake the current shape and pose into a static mesh. Next, we're applying any existing location offsets of the skinned mesh or armature so that the baked mesh will later be in the exact same location. Now we're ready to bake into a static mesh. Let's hide the existing skeletal mesh and rename the new static mesh. We then move it into the Send to Unreal Mesh export folder. Let's start now the export process from Blender into Unreal. We activate it in Blender, and the data comes in very quickly into Unreal Engine. We can immediately open the Mesh Viewer in Unreal and inspect the imported model. Placement in the 3D environment is also very fast. Let's turn on the Play mode in the editor and look at the model from different viewpoints. Let's finish by putting our imported SMPL-X model into a nice environment. Looks a bit empty. There you go. Alright, this concludes our tour of SMPL-X in Blender, Unity and Unreal Engine. I hope you had fun on a little sightseeing trip and that you learned something new. Thank you for your attention and have a great CVPR 2021.